It's recording now. Do you mind if I sit? It's okay. Because I feel like I'm so low and you're like so high. All right, significant figures. When was the last time you've learned this in math?
Like just a few
Yeah.
weeks ago.
Ah, okay. So you've been, I think you also have been learning how to round.
Yeah.
And for some reason, it's simple, but some students just don't. It doesn't tick. But anyway, we also have to deal with significant figures in chemistry because the number of digits reflect the precision. Remember, in chemistry, we measure volume, we measure mass, we calculate stoichiometry because measurements are important when we have chemical reactions, and we do. And if we have measurements, we have to be precise and accurate as possible because that point zero something means a lot already in concentration, for example. Okay, so but keep in mind, the greater the number of significant figures, the greater your certainty. So for example, if I tell you this pen is 29 pesos, so you're sure it's 29 pesos. But if I tell you it's 29.75, that's even more precise, right? I have like the centavos part. By the way, I'm using the slides from the past 2-year reports, last year and 2 years ago. So I collated it and I kind of simplified it and just included what you need to know. Anyway, this is what Tewu wrote. Put their Tewu store. Normally, National Bookstore, you pay 30 pesos and they don't give you a change, even in grocery. That's just, it's 25 centavos. Why do I have to give it back? But in chemistry, that 0.25 means a lot already in our calculation. So when we calculate, we want to express to more significant figures because it means we're more precise. Just a quick example, if we use the digital balance, the blue digital balance, it only goes up to 2 significant figures, right? Like 1.05. So last time in our magnesium lab, I asked you to measure it using the analytical balance. How many decimal places? 4. So I want to have as much significant figures as possible because it's possible that they're 1.00 here, 1.000, but if we use more significant figures, one can be 1.0005, one can be 1.0030. In chemistry, small amounts, big deal, because we're looking at moles, right, which are very, very small. Okay, well, why did I have to talk a lot? Just one page. So in daily life, how would you feel? That's fine. But in chemistry, how would you feel? Wow, that's a big error already. So just a review. How to count significant figures. These are the rules. In case during the lab you forget, I also have it here. I had it here. So I have to just print it again for you. But anyway, just to review, any digit that is not a 0, it's significant. So this is 5. This is 1, 2, 3, 4, 5, 6. 0 in between non-zeros are significant. But zeros preceding a number in the decimal place, it's not significant. So 1, 2, 3 only. Okay. But if the 0 is after a non-zero number, so like right here, it's significant. If it's after. If it's before, non-significant. Maybe the best way to remember this is before your x. It's not important. But after, well, it's important. I don't know why I thought about that. But that's easy to remember, right? Before, don't worry about the zeros before the number in a decimal place. Okay. And then here, remember, before is not significant. So 1, 2, 3, 4, 5, 6. 6 significant figures. For numbers that do not contain decimal point, the trailing zeros may or may not be significant. So for this one, there's no period. So this can be 1, 2. This can also be 1, 2, 3. This can also be 1, 2, 3, 4. So how do we fix that? Huh? Well, okay. Well, using scientific notation, but you can also put a period, right? Like a period. But to avoid that, use scientific notation. For scientific notations, open your books, please. Some of the examples are there. So for page 264, I think those are Some examples. Let's try to apply our rules. You're looking at the table right now. Okay. Um, look at there's a asterisk in the bottom of the table. This is a problem when you don't put a zero. So if it's a trailing zero, 300, 300, that's just one significant figure because there's no zero. So how can we put the zero? It means it's too weird if I put 300 period. So how do we avoid that? Scientific notation. 3 times 10 to the negative 2. So as you can see in the bottom of the table, 300 now. If you express it in scientific notation, that's one significant figure. Okay? Looking at the first one, how many significant figures? That's scientific notation too?
Yes.
Yes?
Why is 300 one significant figure if the zeros come after the three?
There, for scientific notation, 300 is the zero disappeared. 3 times 10. So we don't count the 10 to the second power, just the 3 there. That's why if we have numbers that has trailing zeros, put scientific notation right away. It's easier. It's easier to express. And look at the first one. 135.680. That's how many significant figures? That can be 6 or 5. Right? That can be 6 or 5. So to avoid, because you don't know whether it's 6 or 5, then just put scientific notation. 1.35680, that's for sure 1, 2, 3, 4, 5, 6 significant figures. And then for the next measurement, 620, the zeros preceding is not important, so 3. When you write it in scientific notation, you can also put 6.20, that's still 3 significant figures. 6.00 kilograms, that's 3. Remember, 00 in a decimal. If it's after a number, you count it. And then the rest, okay? If you're not sure while you're calculating, you can just ask me or you can refer to this poster once I print it and put it here. All right, why do we want to learn significant figures again?
Yeah,
Accurate? Did I use the word accurate? Precise. Because there's a difference between the two. We will learn soon. So to be more precise, because we want to express our data as many significant figures as possible, because it means we're more precise if we have bigger significant figures or larger number. All right, so some rules. When we add or subtract numbers, how do we express the significant figure? So we express the number of significant figures based on the least number of decimal places. So what do I mean? So look at this example. What's the least number of decimal places? 1, 3, or 5? 1. So this one should be expressed as up to the first decimal place. Get it? Easy? Another example here. Sorry. If you're subtracting, the same thing. So the least number of decimal place is 3. So I have to express this up to 3 decimal place. Now, why is that important? Well, if I express it as this number, for example, I didn't round it. The problem is, for this number, you're only sure up to the 3rd decimal place. You're not sure to the 4th and to the 5th. So when I subtract, why suddenly you're sure to the 4th and to the 5th? You get that what I mean? You're only precise up to the 3rd decimal place. So where did this number come from? I'm not sure at the 4th and at the 5th decimal place. So that's why we base it on the least number of decimal place. All right? How about for multiplication and division? So it's different. For multiplication and division, we express our final answer based on the least significant figure, not the least decimal place. For example, this is 5 sig figs. This is 4, 1, 2, 3, 4 sig figs. So it should be expressed up to 4, right? So 1, 2, 3, 4. Never mind that. We're not sure at this point. So 3108.8 is round to 3109. So I hope we don't have problems with rounding. Yeah, no problem with your batch. I remember Ms. Girardi complaining last year because some students can't really round. If it's like 5, they don't know whether to round it up or to round it down. Okay, so another example here, if we're dividing 1, 2, 3, 4, 5 sig figs, this is 1, 2, 3 sig figs. So we have to round up to 3. So 4.12. 5 round up. Okay. Review. Addition. Turn and talk, please. Talk about the rules. 1, 2, 3. Just talk it out so you process it. Very good. All right, good. So uncertainties and errors in measurement and results. So let's begin. First of all, in chemistry, we either do qualitative analysis or quantitative analysis. So qualitative analysis, we normally identify the property of your substance, like for example, what is its boiling point, what is its solubility, what is its molar mass. These are things that doesn't change. Like for a substance, they always have a solubility number. They always have their specific boiling point. Obviously, the molar mass doesn't change. Per mole, you already know the molar mass is given. So most of the time, we deal with quantitative analysis. So this is the amount or concentration that can be expressed as a numerical value. So once we do chemical reactions, we can follow quantitatively analyze what is the mass loss of the reactant, for example, or what is the mass gain of the product, how many volume of gas is produced, what's the final concentration. So we're dealing with, in chemistry experiments, quantitative analysis. Somebody waved at me. All right. So quantitative analysis, example, mass, concentration, amount, length, density. We only had one experiment so far, the magnesium ribbon. So that was, we're looking at mass analysis. And we have 2 more on Tuesday. That's why I want to talk about error so we can apply it to your next 2 experiments. Okay, now in chemistry, in any experiment, there's always errors and uncertainty. Like we can't get rid of errors. In other words, we're never 100% sure that we're always accurate and precise. We always have errors. Where are the errors going to come from? Okay, I'll discuss where the errors are going to come from. Before that, let me clarify, Bailey, the difference between precision and accuracy. Let's go straight to this one. So pretend, do you play dart? Okay. There should be like a dart club. It's fun. Where is my pointer? Where is my pointer? Here. All right, just by looking at the diagram and the descriptions here, can you suggest, can you turn and talk? What's the difference between precision and accuracy based on that diagram? Okay, just look at it first.
Precision is how close you can group your things together, your results together.
Mm-hmm.
Accuracy is like the closer to the result you want to find.
Okay, very good. So accuracy is if you hit the what do you call that in dart? The red. The bullseye. The bullseye. Bullseye. So if you hit the bullseye, that's really what you want to measure. That reflects accuracy. If you keep doing it and you always get the same result, you're very precise. That's good. But you're not accurate. You're not accurate. It's also possible that you may be accurate. Look at that. 7 times. About 4 of the 7 times you hit the bullseye. But are you precise? No. So in experiments, if you have repeats or trials, every time you repeat it, you want to have precision. Precision is if you do it again, it's the same value. Do it again, it's the same value. Chemistry, you have to do it at least 3 times and get three consistent numbers. So in the future, when you're doing experiments, if you do it 3 times, one is really off, I will say do it one more time because I want to have at least 3 close values because that means you're precise. Okay. Now, at the end of the day, Miss, I'm really precise. Okay, let's compare it to the actual value. But you're here, you're far from the actual value. Something is wrong. You're not accurate. You're really precise, but you're not accurate. So how do we fix this? Um, I'll discuss this in detail shortly, but right now, let me just say that to be more precise, again, just repeat it. Repeat it several times and give me 3 consistent numbers. Miss, how do I become accurate? If you're always precise, your method seems to be okay. What could have caused your error to be what could have caused your values to be very far from I have to laser here because they can't see where I'm pointing at. Or here. What could have caused your data to be far from here? Can you guess? Maybe you can guess the answer.
Errors.
Let's give an example. For example, the magnesium ribbon. Your empirical formula, you always have MgO2. MgO2 when you're calculating instead of MgO. But Miss, I did it again. It's still MgO2. It means you have excess oxygen. What could have been wrong?
Magnesium strip. The whole thing was like maybe you didn't like sand it.
Very good. Maybe you didn't sand it like how Alexa sanded it perfectly. So you didn't sand it. So no matter how many times you repeat your procedure, if you keep that procedure error of not sanding it, you're always going to be precise but inaccurate. Okay. So in other words, what could have resulted to this one? There's something wrong with your process or there's something wrong with your equipment. I'll explain more about that. So, first of all, there's 2 types of errors, systematic error and random errors. If I forget, I'm going to say it now. Systematic error, if you have a systematic error, if there's something wrong in the system, in your method, in your equipment, it's always going to affect your accuracy. If your method is always wrong, if you have an error in your procedure, if you have an error in your choice of equipment, if you have an error in your instrument, you're always going to be far from the true value. You're going to be somewhere outside. Very precise, but far from the actual value. So the second type of error is random error. Random error is, what does random mean?
There's no pattern.
There's no pattern. It's just random. It happens. No matter how much you want to control it, it just happens. So how can I fix this, Miss? It's a random error. How can I spot that error? Well, there's no way to eliminate random errors. I can, however, minimize random errors. How can I minimize random errors? Do it again. 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 Get a consistent 3. Then you have minimized the random errors. Okay? Just to go back to the previous example, systematic error. How can I fix it? Change my procedure. So sand my magnesium ribbon. Change my equipment. Maybe I'm using something that's not calibrated. So the machine itself, the 0 is not 0. So change your equipment. Change your procedure. You can eliminate systematic error. Random error, you cannot eliminate. You can only minimize. Just do more trials. So in biology, you're supposed to do at least 5 trials or repeats. For chemistry, just 3. All right, so a little bit more detail. Systematic error. There's a problem with the design or the procedure. There's a problem with your instrument. And systematic error will affect your accuracy. I can eliminate it if I change the procedure or the equipment. Remember, if you have a systematic error, something is wrong with the equipment, something is wrong with the procedure. This one also needs exclamation point. There you go. Because if you don't change your equipment, if you don't change your procedure, whatever you're measuring is always going to be either greater or less than the actual. Not greater, how do I say this? For example, for reading the volume of a liquid in a graduated cylinder, for example, you never look at it eye level because you're too lazy to go eye level. So what you do is you look at it from the top. When you read it from the top, that actually results to parallax error. So if you're reading it from the top, pretend this is your eyes, you're always going to be measuring this volume. Okay? So that's a procedural error, meaning I always read a volume less of what it actually is. Another example, if in your digital balance, you know, like when you have to press the zero always. If you don't zero it, you're always gonna get higher than normal values. So for systematic, your number is always going to be either always really high or always really low, depending on your error. So let's look at some examples. That's the first example, procedural error. You don't know the proper procedure of reading liquids in a container. We know the lower meniscus already, right? Or should I talk about the lower meniscus? Do you know what meniscus means? What do I mean? The curve, yes. If you see the curve, it's not just the curve, there's actually double curve. It's like two layers. You look at two layers. Always look at the lower meniscus and look at eye level. But some students look at the eye level. Eye level, and then they saw, because they saw me, okay, Mrs. there. So eye level. You're eye leveling it, but they're doing it like that. So, pointless. It has to be flat surface and then eye level. Another example is here. It's not me, the students. I think that's a curse word. Excuse me, it's not me. It's the students. It's the bad word right there. We are going to be titrating next week. So remember when I showed you the titration, one tiny drop changes transparent to very light pink. And then a drop away, just a drop away, that's maybe 0.01 ml, it turned really deep red. So that's over titrated. Now, if you keep measuring the endpoint when it's over titrated, you're always measuring more volume than what you're supposed to be measuring. So there's something wrong with your procedure. There's something wrong with you. Why did you think that this is the endpoint? This is the endpoint, light pink. So if you keep doing it like this one, your endpoint is the really dark pink, then obviously your calculation will be inaccurate. It's going to be far from the true value. Okay? Other examples. Sorry, I'm spending time talking about this because when you do your experiment, you have to think, what kind of error is that? Is that a systematic error? Is that a random error? All right. Instrumentation errors, for example, leakage or faulty calibration. Most of our instruments, the digital instruments, need to be calibrated, like a pH meter. You have to calibrate it first. Calibrate sets the standard at 0. So if you don't calibrate it, or if you don't zero it, then you're always going to have something really high or really low. Another example is poor insulation. This is where we learn calorimetry. Maybe I can search bomb calorimeter. We will learn this in topic 5, but I'll just introduce it here. Pump calorimeter can measure the the heat value of a substance. Or in street science, that's what we call calories. If a food has high calorie, it means when I burn that food, there's so much heat that is produced. You can try to burn, for example, French fries. It's gonna keep burning, and then, so Miss, how do I measure the heat of that French fries? We're gonna have an experiment on it. Let me show you what I'm talking about.
Also, a bomb calorimeter that measures how hot the bomb is.
Yeah, it measures how hot the liquid becomes when I'm heating my sample. Very good, baby. So last year I asked them to pick any 3 chips from the cafeteria. So this one, example. So he measured the sample, Nova Piatos and bread pen. Then he measured some water, and you measure the temperature of the water, and then you heat your sample, and all of that flame or heat is transferred to the water. Okay, so the concept is, if the temperature of water, well, the concept is the food that you're burning, it transfers heat to the water. So the higher the change in the temperature of the water, the more heat the substance has. Okay, so how can I have errors here? There's a really obvious error, right? Hold on, right there. What's my error here? Do you think all of the heat is being transferred? No, right? No, the flame is here on the side. Some of the heat can actually evaporate here. Also, if I heat the water, some of the heat is heating the metal, not the water. So that's poor insulation. My bomb calorimeter is not fully insulated. Yes, I'm transferring the heat, but not 100% efficient. It's lost here in the environment. It's lost as it's being absorbed by the metal itself. It's not fully transferring to the water. So what you can do is to set up a bomb calorimeter, like this one. So this is your water sample. We have bomb calorimeters. It's just basically an equipment to make sure that all of the heat is kept in an enclosed area. Nothing is lost. So you put your food sample here, and instead of burning it, you can use a power supply to start heating it up. Then as it heats up, this is a metal. So as it heats up, the metal will heat up, and the metal is surrounded by water. So this is a better way to do it. That way, all of the heat, as this is being charged by your power supply, is transferred to the metal, which is directly transferred to your water. So if you did this, that's a systematic error. I'm losing a lot. So I'm probably getting lower volume, lower temperature of water, always lower than the actual temperature change. Okay, another example. Poor insulation, wrong reading of the meniscus, irrelevant evaporation of a liquid substance. I don't know what to say there. Side reactions. I don't know what to say there. Personal errors is the over titration here. So if I said too much, just always remember your systematic error. There's something wrong with your equipment. There's something wrong with your procedure. In other words, change your equipment, modify your procedure. Now, random errors, it just happens. You can't control it. It's caused by uncontrolled variables, cannot be eliminated, and therefore it affects your precision. But to make sure that you are precise, then just repeat it, because this is something you cannot control. So repeat it. Example is reaction time. In biology, you did this when you timed the saliva starch iodine. When it turns to the color, yeah, ideally you have a stopwatch. When it turns, like you click it. But some people will have different reaction times. Like I will have a slow reaction time. One of my students did an experiment on. There's like a game. Have you tried this? Let's try because
What
um,
is it?
the color and the was it the color and the name reaction? Yeah, it tests your reaction time. Let's try. I'm pretty sure you have a faster reaction time than me. So use this test to find out how fast you respond to different colors. All right, let's see. Hello. Ah, no, it says here in the bottom. Start. Let's do reaction time. Reaction time online game. Online test. Okay. What is this? Click to start. Click here on green light. You do it after me, Alexa. Oh, I'm getting faster. Click here. Oh, huh? Click to continue and then you wait. You want to try? So mine is 0.9. Start over. Ooh.
I'm like trying not to blink.
Bailey, you're next. So I know I'm the slowest. I know to myself I have a very slow reaction. Okay. Yes, you're higher. You're 0.3488. I'm 0.9. Okay. Bailey, you want to try? Belize! No, not yet. Click here to start. Like 3 points or 0.39? It's funny
So-
because I feel like I'm as fast as you, but I'm not.
Yeah, I mean, I thought you looked pretty fast.
Yeah. Ooh, point
Wow.
2. Wow. Okay, boys. Dominate the world. Ah, okay.
Ooh.
We got it.
I'm so concentrated.
Sure. Okay. Whew.
I was concentrating
So-
so much.
Imagine if in a group, 3 of us are doing it. Obviously, we're not gonna have the same. So we have to just keep doing it. And even if it's just you, like Bailey alone, you never get the same reaction time. So, in experiments, that is an example of a random error. I cannot make Bailey click it at the same point something something times all the time he repeats it. So the only way I can minimize that is I have him do it several times and get the average. Okay. Another example is when you approximate the mass or the volume. Like for example, this one you're reading and it's like you don't You know how like our gradation goes up to like, for example, this is 1, 1, right? But what if it's here? Most of the time we guess, I mean, estimate. But yeah, guesstimate. We guess by estimating. So that is a random error. I always guesstimate the weighing scale. Like, so you step on the weighing scale and I try to look this way because it looks lower. If you look this way, what? It's 5 pounds heavier? No, no, no. This is the best way to do it. So that's the random. Why are you laughing at me, Bailey? You're gonna be fat too in your life when you're like when you turn 30 or 40, your metabolism is gonna slow down. Okay, so two types of errors, random and systematic. Random error affects your precision. Systematic error affects your accuracy. All right, now let's go to error propagation. So when we do experiments, sometimes we have series of measurements to calculate for a number. So if your series of measurements has its own errors, then we have to propagate. Do you know propagate? The word what do you know what propagate means? Propagate. Disease. Ah, okay. The disease propagates. It means it develops but opposite. It worsens.
Yeah.
Propagate. Propagate. What does it mean? It grows, right? It grows. There you go. It spreads. It grows. So one little tiny inaccuracy can spread into much more errors. So how do we propagate errors? How does the errors grow in our calculation? First of all, let me talk about absolute uncertainty. Absolute uncertainty is the margin of uncertainty of your given result. For example, you measured using this digital balance, 3.56. So you're not sure up to the second decimal place by 1. Okay, rule. It's right here if you forget. Digital equipment, it's always 1 plus minus 1 of the least number that appears on the measurement. If it's analog, it's always half of the least gradation. Miss, what is analog? Like your equipment that doesn't need electricity. The graduated cylinder, for example. Where's my graduated cylinder? But I'm going to explain why instrument choice is important. For example, you use this to measure 100 volume. What is the least gradation here? 50, 75, 25, 125. What's the least gradation? 25. So what is half of 25? Because it's half of the least. 12.5. So I'm measuring 100 ml plus minus 12.5. Is that good? No. That's a large margin of error. So when you measure volume or mass, you want to choose So, when measuring chemistry, you want to use, for example, you need 80 ml. So you will choose 100, right? The least gradation here is 1. So what is half of 1? 0.5. So I'm going to get 80 plus minus 0.5. And you're like, Miss, then let me get the smaller one. Because 50, what's the least gradation? 5? 10, 9, 8, 7, 6, 5? 5, 10, 11, 12, 13, 5. What's the least gradation?
Oh,
It's
0.5.
Still 0.5, right? Still 0.5. But here's my point. I'm measuring 80. Can I go like, Miss, then I'll measure 50 first? and then I'll measure 30. I just added the 2. You may, but that's not ideal. Why?
But then you have to get the.
Not, okay, well, maybe some of the volume is still here. Or,
You still have to get the lowest
Oh,
by
yeah.
50 and then 30. So your people
so you have
margin will be
2.
yeah.
So you're going to add. The first time I do it, I have 0.5 error. And then I did it again, I have 0.5 error. So my error becomes 1.0, right? So we don't want to do that when we're measuring. So always choose the smallest gradation. If you need 8 ml, for example, can I still use this 8 plus minus 0.5? That seems okay. But look at this one. This is even more even smaller. Let's see. Not 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 1. I'm confusing myself now. 10 ml. So this is 0.1. What is half of 0.1? 0.05. I'll use this because I'm going to get 8.00 plus minus 0.05. Okay? So choice of equipment will determine your absolute uncertainty. Remember the rule? Digital plus minus 1 least. Analog, all other equipment, half of the least gradation. All right. So the absolute uncertainty can also be expressed as a percent uncertainty or relative uncertainty. For example, I did 80 ml. Earlier I did 80 plus minus, he said 0.5. There's something wrong here right away. What's wrong? No. I'm certain up to the ones. But my uncertainty is up to the first decimal place. So how do I express this? 80.0 plus minus 0. Yes? So this is called the absolute uncertainty. So if I convert that to percent uncertainty, that's 80.0. How many percent is 0.5 of 80? So calculate it please. 0.5 divided by 80 times 100. Yes.
0.625.
So you can express your uncertainty into absolute or percent uncertainty. When I do the air propagation, you will realize that I need the percent uncertainty towards the end. Anyway, I'll show it to you soon. Okay, here we go. Propagation of uncertainty. So what do I do with the people who are not here? Can I do iPhoto? Will that mirror? Maybe I can. All right, so the people who are not here, look at the next video of the pictures of our calculations. Anyway, this is the given. We're gonna propagate our errors here. Actually, you know what? Listen to me and look at my calculation after. Okay, so we're gonna do a titration experiment next week. Remember, the concept of titration is you have a known concentration of your base. After titrating, you can calculate for the volume. You know the concentration of the volume, you can calculate for the mole. If you know the balance equation, the mole of your base, you will also be able to measure the mole of your unknown. You know the mole of your unknown, and you know the volume of your unknown, and then you can calculate for the concentration of No. Okay. So some error propagation here. So these are make-believe numbers. I came up with these numbers. For example, you did your titration, again, I said 3 times, right? So the first time, that's your initial final volume. Second time, final volume is 22. Third time, final volume is 33. So how will your errors propagate here? There's so many errors already. Why? Reading that in your burette has an error already. Reading this has an error. And you do it 3 times, that's propagating errors. So let's do it the first time. So 0.0. I need your calculator. Initial. Plus minus 0.97%. Step 4. If you know the mole, did I give the volume? I didn't. All right, pretend this is, not pretend. For example, this is, let me just edit this. Volume of a known acid is 25 ml. So the volume is 25 ml. What did you use to measure it? Maybe this, for example, this one. What's our error here earlier? 0.5, right? This is by 1. Please pay attention, 0.5. So 25 plus minus 0.5. How many percent is this? 0.5 divided 25 times 100? 2%. So if I convert that to dm cubed, this becomes 0.025 dm cubed plus minus 2%. Okay. So step 5, let's calculate for the concentration. You have the mole, you have the volume. Mole over volume. Your mole is 1.097 times 10 to the negative 2 plus minus 0.97%. Your volume is 0.025 plus minus 2%. So divide, please.
With not with the percent, right?
No, just
0.4388
8. Huh?
or 0.14.
Okay. We're dividing. What's our least sig fig? 3. Before, don't think of your before.
Oh,
So 1, 2. 0.44 mole dmq plus minus, add this to this, 2.97%. So your concentration of your acid with the error propagated is 2.97%. Okay, this is simple error propagation. What other errors can we find here? Burette. I think that's it. Okay, so what does that mean, Miss? What does that mean?
You can add and subtract 2.97%.
Around, so up and down. Okay. But what does this mean with our accuracy and precision, systematic error, and random error? Next, we have to calculate percent error. For example, the true value of my unknown is 0.5 mole per dm cubed. That's my actual value, 0.5. What is percent error? So how far are you from your actual value? So average your measured value minus in theory divided by your theory. So 0.44 minus 0.5 divided by 0.5 times 100. What's our number, Alexa? 12? 12%. Okay, how do you know if you're accurate? how do you know if you're precise? Therefore, how do you know whether it's systematic or random error? Okay, here it says, fourth bullet point, if your percent error is greater your uncertainty, percent uncertainty, this is a systematic error. Let's see. If the percent error is greater than the uncertainty, it is, right? There's something wrong with your procedure. Miss, that's too small. I know. But then if I get the percent error, this number is too far from the actual value. Makes sense. But if, let's say this is 2%, meaning you're really close to the actual value, and this is higher than the percent error, then this just have resulted from random errors. Okay? Any questions? I hope you remember that. It's all here. If your percent error is less than your uncertainty, then those are just random errors. But ours is 12. That's really big. But if you don't calculate, look, it looks close, right? It's close. No, it's not. That's 12%. It basically means your actual value, how do I say it? If I acknowledge all the fluctuations, all the personal errors, all the random approximate error, it should just be 2.97. That's in other words, it's acceptable to have this error. Where did this come from? In our measurements. Here. We acknowledge that we're not sure. 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 We acknowledge that we're not sure because it's just random. You can't really do anything about it. But then our actual value is far from the true value. 12%. Really far. Therefore, even if after we acknowledge all of the possible random errors that you can't control, still, you're too far from the actual value, meaning there's still something wrong with your system, procedure, or
So
instrument.
if the percent error is far away from the actual percent,
This one?
yeah, if it's far, doesn't mean that it affects
Far
the,
high or far low? Like up higher?
like yeah.
Okay.
Does it affect the accuracy or precision?
Alright, good question. So for this one, since I know it was a systematic error, remember earlier I said systematic error results to inaccuracy. You're not accurate. But you are precise. You're precise, but you're far. But let's pretend this is again 2. So you only have random errors, meaning keep doing this again, and you can be precise. Easy to understand, but you'll forget. I really know you will forget. So, can I make a table for just to try to understand? So for systematic and random, this is equipment or procedure. This is, it's just random. Systematic will affect your accuracy. Random will affect your precision. So what do we do? Change the procedure or equipment. Here, just repeat several times. Rule percent error is greater than percent uncertainty. That means you have a systematic problem. Percent error less than percent uncertainty, it means you're okay. Just repeat. Yeah? Okay, you want one more sample, air propagation? Let me just stop this. Let me finish this. This is like just a few more slides, and then I'll give you one more problem for air propagation. Okay, why? This is just the nature of science. Why is it important that we have accurate and precise measurements in chemistry? So once upon a time, there's what you call an opera experiment. Opera stands for something like, what's it, operational something, electron, la la la. Opera CERN.
Isn't CERN the one?
Switzerland, Geneva.
Yeah.
Yeah. There's 3 particle accelerators in the world. One of them is in CERN. Wait, opera, CERN. What does opera stand for? Oscillation Project with Emulsion Tracking Apparatus. Okay. So in English, they're trying to research subatomic particles. So they have discovered neutrinos. So to simplify this, when your elements start to decay, they can either have alpha, beta, or gamma decay. When they undergo the decays, they lose parts of their they lose electrons, they lose protons, or they may lose a neutron. So what they've discovered is if an element undergoes beta decay, and if they calculate the change in mass, they only look at the lost electron. There seems to be something else that's missing. Like there's a mass change that they cannot account for. So they predicted there might be some other subparticle. They call it neutrinos. It's like an electron, but it's not charged. Anyway, so they're predicting that elements also contain a subatomic part called neutrinos. And then the CERN Research Institute, they did an experiment and they found out that neutrinos travel faster than the speed of light. Okay, slapped to the face of Einstein that said nothing is faster than light. So for some time, they were really justifying their results. There's no errors, whatever. But recently, they acknowledged that there was an error in their calculation. So a calculation error could mean a change of a theory. If they didn't say that they have a calculation error, then we will accept that neutrinos is faster now than light. But when they took into account all of their procedural errors, they calculated that neutrinos travel about the same speed as light. So, nature of science is if you have a flaw in your experiment, you have to account for it. Because maybe, yay, let's say this is higher boiling point than this one, yeah, but then you have a lot of errors. So if you compound that error, it's not really accurate. It's far from the true value. Okay? That's what it means here. So in science, we have to be precise, we have to be accurate, and we have to look at how we propagate the errors because it's going to change the meaning of our final result. There's another story. I think it's not here. But it's in your book. I was reading it. I'm like, oh my. Page 263. So in 1998, NASA launched an orbiter in Mars. So it can it can analyze the atmosphere of Mars. But then as it was going closer to Mars, it completely disintegrated. So, okay, it wasn't able to fix itself and orbit around Mars. You know what the problem is? I was laughing. At end of the story, it says, it was subsequently reported that one team used imperial units while the other team used SI units. Obviously, feet and meters, it's different. So they're both in the States though, Colorado and California. So they're communicating. Because when you like try to land a spacecraft, in other planets, you have to calculate the speed, the velocity, and the trajectory. So one is using a different unit, one is using a different unit. Then maybe instead of like a smooth parabola, it's too steep. They will be just because they're not using the same unit. Anyway, so nature of science here again. That's an impact of an error because they're using different units. Like if I use cm cube here, obviously my mole is going to be much bigger, which is very inaccurate. So I have to be consistent with your units. Okay. In chemistry, we also make use of graphs to show correlation. I don't know if you've, yeah, this is like algebra, grade 9 or 10, right? Basically, your x-axis, that's your independent variable. Your y-axis is your dependent variable. So as you keep increasing your independent variable, let's say, for example, your independent variable is temperature. So as you keep increasing the temperature, what's happening to the volume of the gas? Does it also release more gas? If you plot your data, we normally put we normally use scatter plot, so that's the individual results as you keep increasing your independent variable, for example. And this is a good example of a correlation, right? Because I can obviously see that as I increase the x, the y also increases. This one, as I increase the x, my y decreases. So this is a positive correlation. This is a negative correlation. But look at the middle one. It looks scattered. So there is no correlation. In other words, my x is not affecting my y. Um, so in experiments, after you plot your scatter plots, look at is there a trend? If there's none, then say there's no correlation. If there is, then plot your linear trend line. I have a good example for this one. This is not bad. My supervisee for extended essay. Final. Okay. So we were looking at her graph. At first I told her, okay, plot the scatter plot. Plot your data, use a scatter plot. And this is what she showed me. Don't look at the trend line. So we're looking at the scatter plot, and I'm like, it seems to be having a correlation, right? So I said, okay, plot the trend line. So we plotted the trend line, and yes, there's a decrease in the trend line. Now the steepness of the trend line will show me the strength of the correlation. Y equals mx plus b. Sounds familiar? Slope. If the slope is big, it means it's steep, right? So I told her, plot your formula, get the measurement of your slope. The higher the slope, the more steep the line is. So this experiment is about using garlic capsule to lower blood pressure, which is, look, it's good. As the weeks pass by, it seems to be affecting the decrease in their blood pressure. However, she had a graph that looked something like this. Well, obviously there's no correlation, right? Because I cannot see a trend. Although I can plot a trend line, but if I plot the trend line, my individual scatter plots are going to be far from the trend line. You want your scatter plots near the trend line, as close as possible to the trend line. So I told her, no, there's no correlation. But you can use an exponential line here. An exponential line, I don't know in math if you'll learn it. Trend line is if you can see a clear going up or going down. Exponential, I'm sorry, not exponential. Polynomial trend line is if your data seems to go up, down, fluctuates. If your data seems to fluctuate, plot your polynomial trend line. And we saw here that, yes, it was decreasing. Good job, garlic. But after the 5th week, it seems to increase again. So her suggestion was monitor the blood pressure longer, because maybe it's just fluctuating at the beginning. Then maybe after 8th week, you can see a more consistent increasing trend line. So that's her evaluation. Okay, going. Huh? No, she will write it in her evaluation though, because that's 2 months already. So she wrote in her evaluation that there wasn't enough time to see a clear pattern of increase or decrease. All right. So we can also, well, I talked about the slope, right? So the slope is change in your y divided by change in your x. The higher the slope, the steeper your line. Okay. Intercept. Sounds familiar? Okay. Or your line crosses your y-axis. So when do we use this? We use this when we extrapolate. Miss, what do you mean by extrapolate? Have you heard the word extrapolate before? No. What do you think extrapolate means?
Heard it
Okay.
all. Like if we extrapolate, it can lead us to believe.
If we extrapolate, there's no evidence, but you kind of assume something. That's the same thing in graphing. There's no evidence. You didn't measure the amount, but you can assume that it's this number. Miss, what do you mean? Okay, once upon a time, I was demonstrating with you um, chemistry experiments. Excuse my face again and my voice again. Because this is me talking with the video of me talking. I'll move here. Okay. Oops, I'll pause. Yes. All right. Remember when I burned naphthalene balls? I burned it, and then I put the thermometer, and I monitored the change in temperature as it was cooling. Okay. If I ask you what's the boiling point of naphthalene, you can tell. Why? Because when I boiled it, when I put my thermometer, the heat was still escaping, and it's going to the container. It was when I put the thermometer, it was still reading the actual heat. So some of the heat is escaping until I read somewhere here. So my question is, what is the boiling point? I don't know because when I put the thermometer, it starts at 0 at y, and then, well, Miss, can you just measure the maximum? What do you think? If it's boiling point of naphthalene, I boil it. I put the thermometer. You see this? What's the boiling point? The highest? Well, yeah, sure, that's logical. But if I extrapolate, what I mean by that is, so your line was something like this. When I extrapolate, what I can do is, it seems to have a steady decrease, right? So if I extrapolate, you understand? And I look back, I don't have evidence. But my evidence is there's a steady decrease here. So if I extrapolate from my highest point, that's my highest point, and then extrapolate back to my y-axis, at time 0, this is my temperature. Okay? Now, why is extrapolation important in chemistry? Because when we're doing chemical reactions, we don't know what's happening at time 0. How can we know there's nothing happening there yet? You mix two substances, at time 0, nothing. But then obviously as time proceeds, it's creating bubbles, it's creating a new compound. So how do I know what happened in 0? You extrapolate. Makes sense? Good. So, going back, the use of the graph is number 1 to show correlation. Let me just go back. Number 1 to show correlation. Number 2 to show the slope, the steepness, the strength of the correlation. Like, yes, it's going down, but how steep? How fast? How slow? And then third is to get the intercept, the y-intercept, or to extrapolate what happened in time 0. So this is where everything is possible. You know nothing happened, but I can, without evidence, assume what happened in time zero. I love chemistry, right? So that's the end. All right. Sorry to those who are not here. I'm not gonna repeat myself, so please watch this video thoroughly. Let's look at another. Let me stop that.